All right, so there's another level to the method of u-substitution. We know that the antiderivative of a u-substitution looks like some composite function of f of g of x dx. We're going to let u equal the inside function, g of x, and then find du equals the g prime of x dx. And so we can do a substitution. But sometimes there is an inside or an additional variable inside. Sometimes a variable squared but some kind of loose variable, x variable out in your function. And the first thing before you try looking at other methods that we'll be learning in time is to think, well, maybe I can solve for x. So I can find x equals, and now I'm going to get some function in terms of u. Well, now if I look for the antiderivative, then I know that I'm just going to look for the integral. I can plug in for my x, whatever that function of u was that I discovered, and then continue on with my u substitution, so u du. So I've gotten rid of all of this, but I've had to replace this x with some function of u, and I'm dealing all with u variables, so it's definitely an integratable form. So let's do an example. Let's say we want to find the antiderivative of x times 3x plus 1 cubed dx. So this would be a good time to make a side comment. The easiest way to differentiate this, to integrate this, would be to find the cube. Go ahead and cube this binomial, so I get some polynomial, third degree polynomial, and then distribute the x into that polynomial, and then I can integrate using the polynomial tool of breaking it into separate terms. So there is an easier way, easier-ish way to integrate this, but I want to use this problem as an example of what I'm showing here. So just a little side note, let's do a substitution. Let's let the inside function 3x plus 1 be u. So I'm going to say u equals 3x plus 1, which means du equals 3 dx, and I'm going to make my adjustment by dividing by 3. So du divided by 3 equals dx. So now I can replace dx with du over 3. I can replace the inside part of my cubic function with u, but this x is a problem. So I'm going to solve for x here. X equals u minus 1 divided by 3. So now if I make my substitutions, I've got x is u minus 1 over 3 times u cubed du, or dx now becomes du, and remember du over 3 is just the constant 1/3, so I pull that out front. And from here on out, this is a pretty straightforward integration. 3 can be brought out here, so I have 1/9 u minus 1 times u cubed du, and now I'm going to distribute to make it a polynomial. U cubed times u is u to the 4th minus u cubed du, and I'm running out of room, so I'm going to work across. 1/9 times the integral u to the 4th du minus, well, the 1/9 applies to everything, minus the antiderivative or the integral of u cubed du. And now let's go ahead and just find the antiderivative. 1/9, well, this is u to the 4 plus 1, so that's u to the 5th divided by 5 minus u to the 4th divided by 4, and that would have to have a plus c attached to it. Now at this stage of the game, I have to make some decisions. I could find a common denominator. If I did that, I would end up with 1/9 times 4u to the 5th minus 5u to the 4th, all divided by 20, plus c, and 20 times 9, 180. That might be prettier. I think not. I think at this stage of the game, looking ahead, I'm just going to stick with my original form and substitute back in 3x plus 1. So I have 1/9 times u to the 5th, oh, excuse me, it's not u, 3x plus 1 to the 5th over 5 minus 3x plus 1 to the 4th over 4 plus c. One more example, just to make sure we really get it. Let's find the antiderivative of x squared minus 9 cubed times 2x dx. Okay, so first, recognizing that multiplication is commutative, and since I have a multiplication here and a multiplication here, I'm going to pull that 2 out front. Just get it out of my way. So now I'm dealing with x squared minus 9 cubed times x dx, and this looks exactly like our first example now. I'm going to let u be the inside function, x squared minus 9. So du is 2x dx. And then I'm going to adjust for that 2 because I only want x dx. And then something really cool just happened. I thought I was going to have to solve for whatever that x value was. I was going to have to solve my original u for whatever x is here. But I have x dx on this side. And look, x dx is the other thing that I want to substitute for. So I'm actually finished here with my substitutions at least. So now I've got an inside function, u cubed. And then x dx becomes du divided by 2. Well, that's lucky because that's just 1. So now all I have to do is integrate. I have, whoop, I don't want the symbol if I'm integrating. So this gives me u to the 4th divided by 4 plus c. And all I have to do now is substitute u back in. So I have x squared minus 9 to the 4th divided by 4 plus c. So this shows that you want to do your substitution. That's the first place to go. That's your go-to method in this situation. But you want to pay attention every step of the way to make sure what you're doing. I might have, and I could have, made the mistake of solving for du over 2x equals dx, but then I would have instantly found my mistake, because had I done that, when I substituted back, I would have gotten, well, I still would have had the same 2 over 2, because that 2 would have come out, and then I would have had u cubed. But when I substitute for my dx, I would have ended up with du over x. And the whole point is to have one variable here, right? So to do a substitution, so I don't have a u and an x in my problem. As soon as I did that, as soon as I got that, I would have had to look back and go, wait a minute, what mistake did I did? And I would have found the error in my ways. All right, so that's just an expansion of using u-substitution, where sometimes you will and sometimes you won't want to take the extra step of using the u-substitution, the part where u equals some function of x, and converting that to a function of u and plugging it back in.